Lattice energy is the energy released when 1 mole of ionic solid is formed from gaseous ions. It describes the stability of having ions near each other in ionic solids. Yes, positive and negative ions are attracted to each other. They're more stable near each other. They're lower in energy. The lowering in energy that comes from their being together is equal to a constant times the charge of one ion times the charge of the other ion over the distance between the ions. Now, mind you that one of these ions will be negative, so the energy when they come together will actually decrease. Now, lattice energy is equal to the amount of stabilization, or the lowering of energy, so the lattice energy is equal to the negative of this potential energy change. Okay, so lattice energy should be positive, should be larger and larger when you have more and more charge coming together, and the charges will be closer and closer together. So take a look at lithium chloride versus lithium fluoride. Lithium chloride has a greater distance between the nuclei than lithium fluoride. So lithium chloride has a smaller lattice energy than lithium fluoride. It takes more energy to separate lithium fluoride ions than lithium chloride ions because lithium fluoride ions are more stable, being smaller and closer together than lithium chloride's ions. Now this affects the melting point. Being that lithium fluoride takes more energy to separate the ions from each other, it will take more energy and higher temperature to make the ions float freely around each other, bringing sometimes positive and positive ions near each other and negative ions near each other, sometimes creating non-optimal configurations of the positive and negative ions. So as you increase lattice energy, there's also an increase in melting point. It's harder and harder to separate the ions into both gaseous state and into less and less stable liquid state. Now, we looked at lithium chloride and lithium fluoride. Also look at magnesium fluoride and magnesium oxide. Comparing to lithium and fluoride and chloride, there's an increase in the amount of charge. Magnesium is 2 plus instead of 1 plus, having now twice as much positive charge, and now twice as many interactions of every magnesium fluoride so having twice as many interactions between positive and negative ions, there's a much greater lattice energy, and hence a greater melting point. And then magnesium oxide has an even greater lattice energy. We have about 4 times as much lattice energy than for lithium fluoride because we have twice the Q in one case and twice the Q of the other compared to before. So 2 times 2, there's 4 times as much lattice energy in magnesium oxide than in lithium fluoride. And so there's a greater melting point of 2800 degrees Celsius. Yes, decreasing radius or increasing charge leads to increasing lattice energy and melting point. Now, you'll need to be using the Born-Haber cycle for determining lattice energies in some problems. To do so, to determine the lattice energy, you can use some of the information provided to you. Now, the lattice energy, which is in this long one in blue, is the amount of energy to take solid ionic compound and separate the ions into gaseous ions. You can calculate this whole thing using Hess's law. This whole thing, which we'll call delta H6, is equal to the summation of all the other heats, like heat 1 plus heat 2 plus heat 3, 4, and 5. So this is equal to this and that and that and that and that. But what are all these values? Well, this value to turn lithium fluoride solid into separate lithium and fluorine molecule is actually the negative of the heat of formation of lithium fluoride. Yes, the heat of formation of lithium fluoride is the heat to take the pure elements and get the compound. So that heat of formation goes down, but this heat goes up. So this heat 1 is equal to the negative of the heat of formation of lithium fluoride. And then we have the heat required to take the solid lithium and turn it into gaseous lithium. That is the heat of sublimation of lithium. And we have, let's see, the heat to take half of a molecule of fluorine and turn it into a fluorine atom. Now this is equal to half of the bond enthalpy of fluorine, half of the amount of energy to break fluorine-fluorine single bonds. And then finally we have the heat to take gaseous lithium atoms and turn them into gaseous lithium ions. That requires the loss of an electron, ionization energy. So this heat is equal to the ionization energy of lithium, the first ionization energy. But also we have the heat to take a fluorine atom and turn it into a fluorine ion. In this case, it actually has to absorb an electron, which is generally stabilizing. You will recall that the heat of absorbing an electron is negative because it's stabilizing generally. And so that is actually equal to the negative of the electron affinity, because electron affinity is equal to the negative of the heat of absorbing an electron. So we can take the values that we were provided, and we can be a little careful with some of them. So we had to use the negative of the heat of formation of this solid in order to find the heat of the opposite process. We had to take half of the bond enthalpy of a fluorine molecule to get the energy to get just half of that molecule as atoms. And then we had to take the electron affinity and make it negative to find the energy of taking a fluorine atom and getting a fluorine ion. So be careful with these values that are provided to you. And then having all of these now all going in the up direction, we add them all up to find the heat of the reaction, which if you bother to calculate is equal to 1017 kilojoules per mole. Thanks for watching, guys.